So before moving on to analyze our first very simple source of electromagnetic radiation, let's look at a very specific difference between what we actually referred to before as confined waves and free waves. So let's look at the difference between the wave on a guitar string, which in the first lesson we said is an example of a confined wave, which is not really moving anywhere, and a wave like these in the ocean. So we did make a distinction in the beginning. We said that they're very different, that waves in general, depending on are they propagating or confined somewhere, they're very different, but we never elaborated. So let's ask ourselves, actually, what happens if we confine a wave? What happens if we limit, physically restrict the dimensions of a wave? Now, the simplest way we can do this is to consider a string, for example, and to place it in between two walls, so two solid boundaries. So if you take a string and you confine it, it is actually what a guitar string is. So let's consider the simplest possibility of a one-dimensional confinement. So we have a simple one-dimensional string and we confine it. Now, what happens in this process is that essentially out of all the possible wavelengths, all the possible frequencies in which this string could vibrate, in which waves could propagate on that string, we now have only an innumerable number of possible frequencies or wavelengths. So there are still infinitely many, but they are innumerable, so they are discrete. They are not continuous like before. And in fact, we can show that there is a relation between the possible frequencies and the length of the confinement. So if we confine a string on a very, very large, in a very, very large space, they're actually going to be more closely spaced. And if we do it in a smaller and smaller place, the frequencies which it could have are going to be spaced out further. And in this way, we can think of a free wave, in fact, as a confined wave, which has an infinitely large confinement. So increasing the confinement actually allows more and more frequencies, and it turns frequency to a continuous variable. So the relation which we get, and you can see in the supplementary materials how to get this, is that the possible wavelengths are an integer number, or more like 1 divided by an integer number, times twice the length. So we're effectively, by confining a wave, we're restricting and cutting some of its wavelengths, and we're discretizing. So we're only allowing certain integer numbers, or ratios of integer numbers, frequencies, to be allowed in the formation of the wave. Now, these allowed frequencies, or these allowed wavelengths, are usually called the modes of the wave. So if we confine a string in a certain way, it has only certain modes which it could oscillate with. And these modes, they're typically infinitely many, but again, innumerable, not continuously many. These modes are actually all of the possible waves which we can add up in this confined space. So if we tried to get again a function to represent it as a Fourier series or something like that, we can only use those allowed waves on this string or on this confined media to form the new signal. So in essence, a way to explain it is to actually think of a confined wave as many waves which are constantly being reflected off the walls. And so you can think of the certain points in which the wave has maximums as now oscillating upwards and downwards depending on where the reflected wave is passing, whereas certain points will never move, they will never change, because these are the points in which both the one which is going straight, if you like, and the one which is reflected, both of them have their zero in those points, and so there are certain points which are never going to move and which will always stay stationary. Now these points are called nodes, and you will always get one less node than is the integer number of the wave. So if you start with the first possible wave, so n equaling 1, the integer equaling 1, you get no nodes, 0 nodes. If you get to the second wave, you get just one node in the middle. Now, we're not counting the boundaries, of course, because they can also be considered nodes. If you get n equal to 3, you get 2 internal nodes, and so on and so forth. So essentially, the main difference is that we no longer have propagation. So our nodes are always in the same spot. The points which have a maximum amplitude are always the same points in space. The points which have no amplitude at all are always in the same points in space. Not the same points, but again, stationary. So if we look at how energy is transported, it's not. So if a free electromagnetic wave traveling, it was actually transporting energy in the direction of its motion, a standing wave will not transport any energy. So it will just stay there. There will be some energy density in that point, but there will be no transport. So if we take the Poynting vector, if we look at its magnitude, if we integrate it over the, if you like, over a surface, since nothing is passing through the surface, the wave is just standing there, nothing happens. So no energy is changing. And you may be thinking, okay, but why do we care? How is that important? Well, we'll actually see that it's very important and it allows us to do something else. But just before going there, as another example, the most familiar case of a standing wave again is actually a guitar string. And when you think of the tones which a guitar can produce, if you think of the hand of the player who is playing the guitar, if you think of the hand of the musician as the initial data, so the initial condition, when the person moves the string a little, what he does is he deforms it. He or she deforms the string, and in such a sense, this is an initial condition for a wave equation. And we know the wave equation, essentially. We know that the possible modes of this string are determined by its length. And so moving a little, we can actually solve and we can actually see what oscillations this initial condition is going to cause. But regardless of what exactly they are, we can always be sure that they're going to be a superposition or a combination of all the allowed modes of the wave. And so in such a sense, you can think of standing waves as being the basis or the main modes which you can use to construct new waves. So this was the simplest possible case, just one-dimensional string which was confined in space. But what happens if we confine a higher dimensional surface or a higher dimensional, if you like, volume even? What happens is something very similar. So let's consider the second simplest thing. Again, a rectangular region, but this time we have a two-dimensional membrane, if you like. So this time we restrict the x direction and the y direction, and we have a membrane, what you may call a drum, actually. So what are the possible wavelengths that this thing can oscillate with? Well, the first mode, it turns out that we have similar relations for both the x and the y direction. So the possible wavelengths in terms of x are twice the length of x divided by an integer number. And the possible wavelengths in terms of y are again twice the length in y divided by a certain integer number. Now the two integer numbers are independent, and so you can actually think of them as labeling the different modes, the different possible oscillations. So the first mode, which is 1, 1, it's the lowest possible mode, is when both the integer numbers take their lowest value, 1, and in this case we simply have a membrane which is simply oscillating as a membrane. So all of the points are either up or down, and there are no nodes, what we may call. Now the second mode, second possible modes, and there are two of them, is when one of the integer numbers is 1 and the other one is 2. So just one of the two numbers has gone up. And in this case we get something very similar. We get a division, so the whole membrane is divided in two parts. One part is always going up, the other one is going down, and then they shift. So we have one going up, the other going down, and then shifting again. And this is the type of oscillation we get. Now, depending on do we have 1, 2 or 2, 1, so depending on the integer numbers which label the mode, we have this thing either in x, y direction or inversely, so in y, x direction. But the oscillation is the same. Now, the next excitation, as you may call it, is what happens when you take both of the number to be equal to 2. So this is the next possible mode, and it's called 2, 2 mode. And in this case, we have division both in x and in y. And in this case, we have 4 regions. And again, regions next to each other, we have the opposite amplitude. So when the first region is going up, the second region, the two regions around it are going down, and the last one is going up again. But again, we have this type of oscillations. And if we go further along, we get more and more of this subdivision into regions, and each region is going in one or in the other direction, but each neighboring region is always in the opposite. So these allowed modes are just for a rectangular drum, as we may call it. But what happens is that this is true for any restriction of waves. So for any shape of the restriction. So just for an example, if we take a circular restriction, once again we have these types of modes, but this time they're a little more complicated to describe. On the right you see actually a circularly confined wave. So again you can see that it has modes. It starts with just oscillation like a membrane, which we can call the lowest energy vibration, and then we have the next ones, which again look similar to the rectangular case, except that we have a different symmetry. So instead of having rectangular regions where one is going up, the other one is going down, we have more or less cylindrically symmetric regions where the same thing occurs, but the determination of where they are is no longer governed by the same equation. So it's no longer again the length divided by the integer number. It is something different, which is related somehow to the functions which define the waves in this spherical domain. So these are actually the Bessel functions. They're a little more complicated, but the general idea is the same. So we have confinement, and the waves that can propagate are somehow related to the linear dimension, so to the radius of the circle, but just the enumeration or the modes to give them explicitly is a little more complicated. Now you may wonder, how are we going to use this thing when these waves are not really transporting energy? So what we wanted was to transport electromagnetic waves, but the standing waves are not transporting anything. In fact, they just give zero energy transport. They just have some energy, but they don't move. So how can we use them? Well, the trick and the main application is to restrict only some of the degrees of freedom of the wave. So what we do is we form what is known as a waveguide. So instead of restricting the wave in all of its dimensions, we restrict only one or only two of its dimensions, and we let it roam free in the other ones. So an example of a rectangular waveguide is shown above, and you can see that we have restricted the x and the y dimension, but the z dimension is still free, so the wave can still propagate in the z dimension. And what this gives us is actually a way to control where the wave goes. So it actually allows us to confine the wave and to sort of make it go in a channel. Unlike non-free wave, but one which we got from a source, which goes spherically symmetric everywhere, this wave we can actually transport, and we can actually turn. Or for example, you see here a left turn in this waveguide. And the very important thing which we get is actually a dependence on the frequency. So each waveguide is actually designed in such a way, by giving it specific linear dimensions, that only certain waves will propagate along it. And what is more, it allows us to actually do very interesting things like switch polarization. So if we take and twist the waveguide, we can actually get the wave from horizontal to vertical polarization by simply twitching it by 90 degrees. So we can also do turns, we can make loops or something like this. And you see just in this example of different waveguides that we can do this for all sorts of shapes. So we have rectangular waveguides, we have circular waveguides, we can get square waveguides, and we can get turns, we can get twists, and all sorts of other guiding we may need for our waves. So this is actually something very important, and it is one very nice way in which we can take a wave and we can channel it, if you like, and get it to where we need it before we actually release it as a free electromagnetic wave from the antenna. And this is one way in which we feed antennas, by waveguides. So one important and perhaps conclusive thing to note is that just like we saw for general waves, waveguides have modes, and these modes have specific names. And just to list how a rectangular waveguide is classified, we're going to look at the two main modes which propagate through one. So the condition for a rectangular waveguide is exactly the same as that for the rectangular confinement which we saw previously. So we restrict the x and y direction of the waveguide, and the wave keeps propagating in the z direction. Now, restricting x and y directions, we get again this relation that the wavelengths that can propagate are 1 over integer number times twice the length of the respective dimension. And what we get are the two modes that we get are actually called transverse electric and transverse magnetic modes. So what they mean is that unlike the free electromagnetic wave, where we had the electric and the magnetic field always orthogonal to each other and orthogonal to the direction of motion, so we had three vectors which were always orthogonal to each other. Unlike that case, when we're in a physical media or when we're in a waveguide, in fact, we could have longitudinal components of the electric or the magnetic field. So the three vectors of propagation, electric and magnetic, they're not always perfectly orthogonal, and they have longitudinal components as well. So the two modes are characterized by the fact that in the transverse electric mode, only the magnetic field has component along the direction of propagation, whereas in the transverse magnetic mode, only the electric field has such a component. And so you can see just a basic sketch of how this looks. This again, it is given completely by Maxwell's equations, substituting the conditions of a waveguide, so the confinement of the waves in Maxwell's equations, it can give you these solutions. But the general lesson to know is that these two separate solutions, so you see on the left, the electric field is only transverse, while on the right, the magnetic field is only transverse. And these two, again, can be thought of as being polarizations. So in essence, these modes, they can propagate independently, and we can view them as the two types of polarizations in a waveguide. And this is important because most waveguides, they have several modes, different modes, and if you know how to work with them properly, you can actually propagate different waves or different wave packets, and depending on the waveguides and the modes you're using, you can do something very similar to what we spoke about polarization. So you can transmit and receive along the waveguide with essentially in the same frequency by using different modes. Classifying the modes for other geometry, so for circular waveguides or even elliptical or whatever else you might need, is a bit more difficult. The functions involved are a bit more complex looking and the relations are not that simple, but the general idea is the same.